Welcome. Today what I'd like to do is I'd like to walk you through the first problem from last spring's final examination in ME 3200. If you recall that the first problem, the first work problem was, as you see here in Blackboard right now. I guess I need to share that screen. Okay. So the problem states a closed system that has a mass of 5 kilograms undergoes a process in which there is a specific internal energy increase of 10 kilograms or kilojoules per kilogram, while the elevation of the system decreased by 3 meters. It's assumed that the velocity of the system remains constant. During the process, the system receives 10 kilojoules of work from an external source. That could be a piston or a paddle wheel or some type of an electric element that has been input into the system, while producing a work of 8 kilojoules. That could be boundary work that is working against the environment, or it could be raising a weight due to some process, some work process. You are to determine the heat transfer in kilojoules and identify whether or not the heat transfer to the system was to the system or it was heat transfer away from the system. So this particular problem is just simply a first law problem on a fixed mass system. What's happening here is internal energy is increasing, and then there is contributions due to work to the system. And what really needs to be done here is just an accounting for the direction of the work, whether it's in or out of the system, as well as then the final answer, which is how much heat transfer had to occur either to or from the system. And so with this information in mind, then, I want to go ahead into our thermodynamic software. This is the test software. You should by this time know how to log into the software. In answering the questions whether or not this is a system, substance, or process, for this particular problem, it's obviously a closed system. It turns out that we really don't have to concern ourselves with the substance, but we are going to pick air as a substance, a typical substance. And then the process that is undergone between state 1 and state 2 then will be where we have some heat transfer that occurs either in or out of the system. And so since it's a closed system, we're going to go to kind of a generic, simple process here. And like I said, we're going to select just an ideal gas as our substance. Now, the one thing we know about an ideal gas is that the internal energy is typically only a function of temperature, a slight function of pressure, but in our case, for an ideal gas, we will assume it's only a function of temp. So our first state, we can go ahead and say that as we go from state 1 to state 2, the mass is 5 kilograms. And since I've picked air or defaulted to air, then we can start off with giving it a temperature and seeing what the internal energy is, because it's only a function of temperature. And so I'm going to go ahead and select in Celsius. I'm going to select an initial temperature of, let's say, 50 degrees Celsius. Now, what you see in the program, the internal energy for this ideal gas at 50 degrees Celsius is a negative 67.5. Don't worry about the negative sign. All that's really of interest is the change. In this particular case, as we increase the internal energy, that minus 67 will become a smaller negative number, which would imply an increase in temperature. What else do we know for this initial state? And the mass is 5 kilograms. We really don't have to give it a pressure, but we could if we wanted to. We could give it a pressure of 100 kPa. Knowing that pressure, then all the other thermodynamic properties are defined. If we then look at what the after state is, we'll call that state 2. We know that at state 2, the mass is the same as the initial mass. It's a constant mass system. And what we were told in the problem is that the internal energy goes up by a factor of 10 units. And so we're going to say that the internal energy started out as U1, and we're going to add 10 kilojoules per kilogram. Upon doing that, one sees that causes the air temperature to go from 50 to 63 degrees Celsius. Again, we really don't have to concern ourselves with the pressure, but we can give it a pressure if we want to. We can say just arbitrarily that it's at a pressure of 200 kPa. That again just allows us to calculate the other thermodynamic properties for this constant mass system. So we've got state 1 and state 2. We now want to go into the process panel. And our process panel then basically allows us to select the before state, which is state 1, it's air, and the final state, which is state 2, again, air. And so what we're really dealing with in this problem, it is a constant mass system. The final mass is the same as the before mass. What we're concerned with in this particular problem is simply the conservation of energy. And as you can see here, we have this mass times an energy value. This would be U if all we had was internal energy. But in our particular case, we have not only internal energy, but kinetic and potential energy, which reminds me that I forgot to include in state 2 the fact that the position of the system went down by -3 meters. And so the Z value for state 2 is equal to the value of Z1 -3 meters. And so what happens is that then causes the energy, the stored energy in the system. So this E, as you can see as I hover it over it, is, you can see up at the top, it's the specific stored energy. And what that corresponds to is that corresponds to the internal energy, the magnitude of the internal energy, any contribution due to velocity or kinetic energy, which is 0, plus a potential energy component, which would be associated with the gravitational constant. And so this internal energy value is going to be different than the energy value right here. If I went back to state 2, in state 2 where we had no velocity and no potential energy, one sees that the internal energy is equal to the stored energy. Had I given this a little bit of potential energy by giving it an elevation, one would see that there is a slight effect of this particular amount of mass, or this mass being raised a certain height. Okay, the gravitational constant's in there, as well as the conversion from joules and kilojoules. And so you see that it's not considerable, but it is in the 100th place here, a slight difference. had I given this a much larger rise in elevation, one could see that the internal energy and the stored energy are slightly different. Same thing holds as if I'd given it some velocity. If I give it some velocity, there's then a kinetic energy term, there is a potential energy term, and you see that those two terms combined to make this stored energy value higher or less negative than the internal energy, because this E is just simply equal to U plus a kinetic energy term plus a potential. So I'm going to go ahead and bring the potential back down to 0, which was our datum. Oops, sorry. And my velocity, I'm going to take that back down to 0 as a datum. And now we're back to the same here. In state 2, because I added some kinetic, some internal energy, this value went up somewhat. And so now we go back to the process panel, and we see that it's really this difference in this stored energy, which includes the change in internal energy, any change due to potential, and any change due to kinetic energy. These are specific numbers times mass. It puts it into kilojoules. And that then from the first law is related to heat transfer minus work. Okay, in this case, we're looking for the heat transfer, and then we have to ask ourselves, what work do we have in this particular problem? Work is divided up into two parts. One is a term that's referred to as W0, which is either shaft work or electric work. That would be work that we did on the system by some external means. In this particular problem, we know we can say that we don't know how that 10 got put into the system as it states in the problem. We just know that it's a combination. So it was 10 kilojoules into the system. So the W0, which we can put in here, is then going to be a negative 10, because our definition of work is positive out of the system and negative into the system. So we basically put in a negative 10 for the W0. Now, the question is, what is WB? WB is the boundary work. And so the boundary work would be as the boundaries move, or as we cause work to be done. Maybe it's a piston center type of an arrangement. That is the 8 kilojoules that was given in the problem. And so the WB would then be a positive 8. Okay, so we have a negative 10 for what we put into the system. We have a positive 8 for what comes out of the system. And so the combination of those two is actually a negative 2. And so negative 2 means that 2 more units of energy went in the form of work than was actually brought out of the system. And so that would give rise to the internal energy change. But it would also, that internal energy change and that work is going to then balance with the heat transfer. So after going through this, and because of the mass of 10 or of 5 kilograms is this, we have this change in the stored energy. The left-hand side then has to be equal to Q minus this term, this combination term. And so the math is done for us, and the magnitude of Q1 then is 47.8. It's a positive because of the equation here, and positive for the first law implies for heat transfer work into the system. So in order for that amount of work that was being done out of the system into the system to cause a rise in the internal energy of 10 units, we see that this amount of heat transfer also had to accompany that process. And so that then answers the question. If we wanted to print out the information, we could then go to the I/O panel, do super calculate, and we have all of our input as long as what we put in for the process. And then we also have our time and date stamped output that we could print and solve for. Okay, that finishes that particular problem.